This is Todd Frazee, and here we are. We're going to do a turning job. This is the Dash 107 cam bushing uh, tutorial, and we're going to load into SolidWorks, our tool library. So if you haven't already done that and you need help with that, there is a separate tutorial on how to load your tool library. So here we go. We've got our part here. It's the Dash 107. And we're going to go over to the tab that says cam, and then we're going to arrow all the way to the right. We're going to select on the it looks like a tool cutter, and here it has our Dash 107 operations. We first highlight the operations, and we're going to make a job. Okay, and it's going to change it from milling to turn or mill. When it says turn or mill turn, that means it's a machine that's capable of milling and turning. Okay, and on a turning machine, you can see that some default jaw, shape of a default jaw, chuck jaw is cross section is shown. We're going to put under the comment here S60-107, and it's going to be turn complete. Okay, because this job itself finishes the entire part in this case. Now we've got our model, and instead of a relative box size, we're going to go to cylindrical because that's the shape we're doing. Now you notice the default symbol is not in the same orientation cylinder as our actual part. Okay, so we need to change the orientation of which direction Z is. Right now the spindle is facing us. So we're going to move over down to where it says work coordinate system. And we need to orientate the stock and the model in the orientation that it would be mounted in the machine, which is Z running along that center axis of the cylinder. So we're going to change it from front plane, Z axis and X axis. So we can take the front plane, instead of having the front plane selected, we're going to select the face of our model. Okay, so now that turns Z and our theoretical lathe chuck in the same orientation. And we want X pointing up. Remember, we're in a slant bed lathe, so all our tools are actually going to be mounted upside down so that the chips go with gravity. Okay, so you could reverse the X. It really isn't going to matter on the code. It's going to come out in the same orientation on this type of machine. Okay, our origin, we're going to put it at, we're going to actually do it at model front. Okay, so we want our origin at model front, and then we'll have a little bit of extra material that when we face this bar off, we'd have a longer piece in the chuck. We face it off, that becomes 0. Okay. Now, let's go back up and set our stock parameters. So 236 thousandths, and we're going to take a 1/4 of an inch and subtract that value from it. So if we're starting off 0.25 stock minus 0.236, we're left with 14 thousandths on either side. So on the diameter we have extra 14 thousandths, but on our radial offset it's going to be half of that. So we're going to put in 7 thousandths. Okay, so you can see that the stock's a little bit bigger than our part. And on the front we're going to add 0.01. We're going to add 10 thousandths to the front of the stock. So it's a when we set our tool, we want a little bit of extra material sticking out. So the front of the stock will actually be at positive Z value 0.01. Now on the backside stock offset, we're gonna put in like 2 inches. Okay, so we got 2 inches of material sticking in the chuck. We're gonna make multiples of these parts out of it. They come in 3-foot bars, so I guess you could put 3 foot, but 2 inches of purchase inside the chuck is a good amount. And then it's asking you how much of that is in the chuck itself. So we're going to say this overall length of this part, we need enough room for a parting tool to come in the back, which is 150 thousandths. So I would round that up to about a 1/4 inch and then add some margin because you don't want to hit the chuck with anything. So let's say that 1 inch and 600 thousandths is inside the chuck itself. You can ignore this clamp inside. That would be if your chuck was actually clamping on the outside of the jaws inside a ring or something. So you just leave that blank. And we have kind of a representation of how it's going to look in the machine, even though we don't have a 3D representation of the chuck. We've got a 2-dimensional outline of a chuck jaw. Okay, and we're scrolling down, and we need our program name. And remember, this can only be 4 digits, so we're going to go with 107.1. And then if we had a second program, it would be 107.2. Okay, so we'll use that naming convention for the rest of our programs. Our program comment is going to be S60-107 lathe. Actually, it's going to be op 1 for the lathe. Okay. And we only have a primary spindle. In some lathes you have a primary and secondary spindle. So we're just going to stick with that. And we can accept that. Alright, I'm going to close this measurement window. And if you want, you can rename the job. So we could call this the S60-107 op 1 for the lathe. So kind of organize it, because if you had multiple setups, you might have op 2 for the lathe, op 3 for the lathe, op 4 is for the mill. You could organize them that way. Now we're going to put in our routines. So the first thing we want to do is establish our 0 on the face and face off the front, because we're qualifying that. You've repositioned this bar and it may not be positioned all that accurately. So once this cut goes in, we know that we're not going to hit anything off the end of the part, because it's going to be machined down to what our model is. Okay, so what we're going to do is we're going to turning, and we're going to use a turning face command. And we're going to go to our library, and we're going to select from our tool library tool number 1, which is our turning and grooving blade. Yeah, you should have built this in a prior assignment. If you haven't, you need to return to the previous unit and build out this tool library. Okay, we're going to select that tool, and this is a very tiny part. So there's our cutting blade. Looks huge there. And it's going to assume that you want to cut on the face of the model. Okay, we want to use constant surface speed. 5,000 seems a little high, but we'll stick with that. Under geometry, I don't believe we need to select anything. Heights. So instead of heights, what this does is it models it in diameters. So you have these different rings for your different motion commands. So the retract command is when the tool retracts, it's not cutting anymore. It's going to be at a clearance plane that's right here. It's this outside ring. So it is, so our clearance is going to move it rapid at 400 thousandths away from the retract plane, which is the smaller ring. So the retract plane, where the tools are going to pull back before they move locally, is based off the stock outside diameter, adding 200 thousandths to that. So that represents this distance from the part. Then we have our, what are we actually cutting? So we're going to cut from the stock outside diameter when it's feeding in, and we're going to go all the way to the model inside diameter, which would be 0. And because this hole isn't here, we want to make sure that we actually go past that a little bit, make sure we don't have a little nub that interferes with the first drill bit. So we're going to actually go a little bit farther, and if you put it in this box, it's a positive value to go that many increments beyond center. So if I put, say, 0.5, it's going to go really far past center. We don't want to do that. So let's put in a 0.01. So we're going to go about 10 thousandths past center, just to make sure that that tool, if it's off a little bit, we don't get a little cone here at the very end. All right, then we're moving on to the next tab, just from left to right. We're going to leave these all at default. If we felt the need to do multiple passes where you had to rough off a lot of material and come back and do a nicer finish, you would change the setting here. On this box, it's for cutter compensation. It's kind of interesting, it's not labeled. We're going to change that to wear. Okay, and what that does is when it outputs the codes, it allows the machinist that's actually running the part to make adjustments based off the wear of the cutter and how the cutter is performing. Okay, so let's move on to the next tab, and it's called linking. So we're going to do full retracts. This is a pretty small part. We're not cutting into some deep areas that we need to move locally through, so we're going to leave that alone. The 45-degree lead in and lead out, I don't like that for this type of cutter. It doesn't cut on its side very well, so if it were to run into something diagonally, it's going to knock the insert out. So we're going to put that lead in at 90 degrees. Okay, and it's 80 thousandths. And then when we retract out, we don't want it the same way. So we're going to deselect this box, and instead of 45, we're going to go at 0. So what we're going to do is we're going to plunge straight in, go to that center point, and go 10 thousandths beyond. Then it's going to feed away from the part, and then it's going to retract out. So hopefully we don't have any collisions there. Yeah, I'm just going to leave this 0.08 at default. It really isn't that big a difference for this small of a part. Okay, we're going to hit OK. And we now have our first routine. So you can see it's green where it's feeding in. It turns blue, which is a little hard to see because of the plane that's orange there. And then it feeds back out, and rapid is yellow, which is barely showing up on my screen, so you may not be able to see the yellow lines at the resolution of the recording. Now, if I stop zooming in and out, we have our first operation. It says turning face 1. I'm just going to leave the name there. You could change it, but that's going to actually show up as a note in the code. Now let's go to the next routine. So after we smooth the face off, we'd want to turn the outside nice and accurately. So we're going to go to turning, and we're going to use the turning profile command here, the very first one. Alright, so we're going to go to our library, and we're going to select our next tool. So right now, what it's doing in your document, it's attaching the tools you're using just in this document. So even if you don't have this full library, it will have those individual tools sold with embedded in the SolidWorks file, and so you don't have to worry about losing those. But definitely save all your files off in your H drive. Okay, so we're going back down to our library, and we're going to use the general turning tool. Okay, and this number 3 is an outside diameter tool, the way we had it set up. If we expand our descriptions, we actually have 3 of those tools, but you notice number 6 and 7, one's left-handed, one's right-handed, but they're called facing turning tools in their description. So okay, so we're using tool number 3. We're going to select it, and it looks monster inside next to this part, even though it's a relatively small tool. And we're going to leave flood coolant. Let's go ahead and leave the constant surface feed. It's going to have a maximum of 5,000 RPM, so the spindle won't go any faster than that. Typically, you would set that to whatever the maximum of the lathe you're running is. So If it's not capable of $5,000, you need to put that lower. Your surface feed is going to go against that to proportionally spin the part. So this is so close to center, it's probably going to be running pretty close to 5,000 RPM. Okay, now we're going to go to geometry, and it auto selects a cross section of the part. Okay, so we're just going to accept that, and we're going to go to our retracts. Now in this case, we want to leave our clearance and our retract alone, but then our outer radius is going to be the stock, but our inner radius is going to be the model OD. So we don't want to cut any deeper than the outside of our model with this cutter. So that's what this blue zone is. In theory, you shouldn't get any cutter path that's smaller than that. Okay, we're going to move on to our inserts here. So we're going to just do one roughing pass, one finish. This is it's actually just going to do a finish pass. There's not enough material to remove there to matter, so it's straight to a finish pass. Again, we're going to change our compensation to wear, and you could repeat the finish pass if you want a spring pass. So if you cut this the first time and it's a little too big, you could select that, and it'll do an extra finish pass, and maybe that'll help you hold the tolerance you need. Alright, so now we're going to go on to the next tab. And we'll leave the minimum retraction alone, and we're going to do a retract lead. We're going to lead in, and we're going to lead in at 0, and we want to lead in off the part. We're just basically doing a straight cut on this outside diameter. So let's lead in by 0.1. 0.1, so we're going to increase that to 0.1, and then we're going to do a different lead out. So we're going to make it a different increment. It's going to be at 0 as well, but we want to turn this past beyond so that we have enough clearance for our cutting blade to come in and start at the outside diameter of the part, not the outside diameter of the stock. So the width of that cutter is around 150 thousandths. We want to go farther, a little bit farther, so we have some clearance. So let's go 180. That'll leave a 30-second of clearance for chips and coolant to get in there, and then we're going to hit OK. Alright, so we have our green line feeding in. It makes our cut, and then it feeds out. So you can see a orange silhouette of what the part is going to look like. It's a cross section when it actually cuts. So we've got our second routine there. Turning profile, outside diameter. Oops, didn't mean to do that. Okay, OD profile 1. And again, that pops up in the code, so if you're on the machine and you're trying to skip to a certain point, you can do that. Alright, our next step is to do some drilling. So we're going to use the standard old drill. I think the drill wizard is, if you don't have the drill set up, it's supposed to help you do that. But we already pre-set up our drills. So we're going to use the standard drill, go to our library, and we're going to go to the lathe tools, and we're going to use the 1/2-inch spotting drill for this. Okay, so we select it, and 5,000 RPM, that should be fine. We're going to go to the next tab. It's which holes are you going to cut. So we only have one hole. We're going to select the face of the hole that's in the middle of the part. If you had multiples, it could optimize it, but that's more on a mill. And then we go to our heights. Now this is converting back to the way it is on a mill, because it's all based off the drill bit being normal to this face. So instead of having the cylinders like we had before, we have these planes. Okay, so our clearance height again is 400 thousandths from the retract height. The retract height is based off the stock top, which when it's saying stock top, that's the end of this part. Now we've already machined that face down, so let's change that to model top. Okay, and the planes will move forward a little bit. And the feed height is going to be from the top of the model. The feed height's based off the top, and the top is defined as the top of the hole. Now you need to be a little careful on this. If the holes have chamfers and things like that, it may interpret the hole inside the part. So I'm in the habit of actually changing this to model top, and then that way you know that that plane is at the top of the hole and not inside the part where the chamfer starts. Okay, now we're going to go, okay, so our machining is going to feed our drill bit from model top to hole bottom by default. We actually, in this case, just want to come in and do a little spot face. We don't want to go all the way to the bottom of the hole. So we're going to change this from hole top, okay, and we're going to go a negative distance. Hole there is supposed to be 196 thousandths. If we take half of that with a 90-degree cutter and go that half that depth, we will go our resulting diameter on the countersink will be the same size as the hole. But one trick is to go ahead and make a little edge break here. So we're going to make it 10 thousandths bigger. So if we take our hole and our finished hole size is 0.096, we're going to divide that by 2, and if we add 0.01, we'll end up with a 5 thousandths chamfer at the top of the hole after the hole's drilled and reamed. Okay, and so that equals 58 thousandths. So we're going to go negative 58 thousandths from the top of the hole. Sorry, it's 58 thousandths, not 580 thousandths. Okay, so we should have just a little short cut there. All right, so we're going to go to the next tab. And what type of cycle are we going to use for drilling? So there's a whole slew of them here. We've got just a standard drill, so it's going to come in, it's going to go all the way to its depth and pull straight back. There's a counter bore, and it goes through slowly. The counter bore does its cut, it stops at the bottom and dwells for a little bit, for a few seconds, then pulls back out. We've got a chip breaker, which means the drill bit goes in and pauses periodically to break the chip up in the material it's drilling. And then we have a deep drilling, which gives you a full retract, and that throws the chip out. Typically in soft materials, that's what you want to use. As breakthrough drilling, where it can change the parameters at the very end of the hole. Guided deep drilling, tapping, left and right hand tapping, reaming, boring, fine back boring. There's all these cycles that output different thread milling, output different cycles. Okay, so for this we're just going to drill. It's going to drill in, wrap it out. It's a very stout drill and it's not going very deep. Okay, so we're going to accept that. And then we've got our V shape. So again, it's slightly bigger than the hole. The rendering isn't going to appear proper for the machining, but you can see this profile reflects a countersink that's a little bit bigger in diameter than the hole we're putting in. Okay, so let's go ahead and change the description of this to spot drill. Then we're going to move on to the next cycle.